All right, so now that we've had these drawn objects, now we need to actually update the position of all these objects. So we have up here, update positions. I'm going to create a method, update position, that I'm going to call here, and then I'm going to create that down here just below draw objects. I'm not returning anything, so void, returning the void. Update positions. Make sure you spell it exactly the same way. Strangely enough, one of the biggest errors that most people have in coding is spelling. Upper and lowercase matter. All right, so now that we have all of our accelerations and all of our velocities, all we're going to do is we're actually just going to go through all of our planets, and we are going to update their x coordinates and y coordinates with their velocities. So make our little for loop to walk through the entire array again. And then I'm just going to update the x coordinate of a particular object with whatever it was before, plus my velocity. And the y coordinate of A plus the y velocity of A. So this is a stepwise simulation. If you think about, if any of you have taken calculus, if you think about what they're doing with that is they're just taking an infinitesimally small piece and calculating it over time. What we're doing is we're just taking larger chunks. So we're updating the position of our objects based on however fast the processor works. So it's just a more coarse version of that idea. All right, so what do we have? Oh, what did I do? Speaking of spelling errors, let's make sure we spell this right. There we go. So now we actually have objects moving around in space. I don't know if you noticed, but some of these objects, when they get close to each other, actually interact. Sure, now I'm going to get a run that's not going to have anything. There we go. So you notice that as they got close to each other, they actually interacted. Now there's a problem that when they actually are too close together, they go shooting off because they actually go inside of each other, and the force ends up getting basically exponentially larger as they get closer. Because as your force equation, as this value gets smaller and smaller, it makes this much, much larger. And when you're close to zero, this gets very large. And so they go shooting off. So to deal with that, what I'm going to do is have collisions. So let's see, what should I call this? Maybe just collision. Another method down here. And by the way, I'm going to be doing inelastic collisions. And for those of you that don't remember, that is the mass of the first one times the velocity of this first one plus the mass of the second one times the velocity of the second one is equal to the resulting object, which is sticking together. So you just add the masses together times whatever its new velocity is. When we have a collision, first of all, we got to better check to see if there actually even is a collision. So let's go through all of our objects. I swear I've done this before. And then I'm going to go through each of the other objects, because I'm basically going to compare every object and say, hey, are you guys too close together? Should you become one object? So just a quick reminder, if the radius of this plus the radius of this, if the distance between this center and this center is less than those two radiuses added together, that means that they're actually colliding. That means the circles are inside each other. So that's when I'm going to consider it a collision. There's a couple things I should guard against first. So I don't want to have an object overlap itself, because obviously it's going to be less than its own radius. So make sure A is not the same as B, so that I'm looking at two different objects here. This is an ampersand. On most keyboards it's on the 7. This means and. So if A is not B and the mass of A is not equal to 0, because I'm going to basically make the mass of one of these two objects 0, and that's how I'm going to consider that they're not part of an equation. And so same sort of thing with the mass of B. If these are all the case, then I need to actually start doing some calculations. So I need to figure out if the distance between them is greater or less than the radius. So I better figure out my difference in x values again. So it's going to be x coordinate of one object minus the x coordinate of the other. Y coordinate of one object minus the y coordinate of another. And if you're wondering, yes, you could combine these equations together. I'm just trying to make the lines of code shorter, and so do a series of lines as opposed to all in one calculation. So the distance is the Pythagorean theorem, square root of the square of the difference x plus the square of the difference of y. One for the square, one for the square root, and away we go with a semicolon. So I could take this equation here and put it in place of this. I could take this equation and put it in place of this. But I think that would make it less clear. So there you go. Well, we better see if this distance is less than or equal to, let's see, what do we need to figure out? The radius of our objects. Well, we calculated the radius to be the square root of the mass, because we're considering area. So square root of mass of A is one radius, and the square root of the mass of B is the other radius. So if we add those two together and it's less than the distance, hey, we are overlapping, and that's not good. So did I get all my, those two match, those two match, those two match? Okay, good. So that means that we need to do our inelastic collision. So what I'm going to do is calculate for this velocity here. So if I solve for this v3, I know the masses of the two objects, I know the velocities of the two objects, and then I'm going to divide by this quantity in order to get my third velocity. I'm doing component-wise again, so I'm just going to consider the x velocity of A, for example, to be one of these things. So what I'm going to do is I'm going to make object A the thing that survives, and object B is going to go away. So this is the mass of A plus times the x velocity of A plus, let's parenthesize all this just to be sure. Computers do obey order of operations, but I like to be absolutely certain just to avoid errors, because sometimes my brain doesn't do order of operations correctly. Divided by the mass of A plus the mass of B. And then basically the same thing for the y velocity. The mass of A times the y velocity of A plus the mass of B times the y velocity of B divided by the mass of A plus the mass of B. Blam! Inelastic collision. Okay. So now we need to make the A object have the mass of both of them. So the mass of A is equal to the mass of A plus the mass of B. And now I need to figure out the coordinates. Basically, I'm going to average based on their mass. I'm going to take the distance between the two objects and average it, except that the heavier mass is going to lean more towards that particular object. So rather than just talking about it, let me show you. So this is going to be the mass of A times the x-coordinate of A plus the mass of B times the x-coordinate of B. So basically weighting these based on the mass, all divided by the mass of A plus the mass of B. Same thing with Y. Otherwise, basically one of the object B would disappear for no reason, and so I'd rather make them look like they actually combine together. There'll probably be a slight jump in my program, but I'm okay with that. These are decisions that have to be made. So we're basically doing the same thing with the y-coordinates. The mass of B times the y-coordinate of B. I should parenthesize things like I said I would. All right. And then finally, in order to basically remove this thing, mass B, from the simulation, I have all these if statements here, where if the mass of B is 0, it's not considered in any of these equations, which is what I want.